Deep video portraits enable photorealistic reanimation of portrait videos. We are the first to transfer the full 3D head pose, facial expression, eye gaze, and eye blinking from a source actor to a monocular portrait video of a target actor. Given an input video, we first track the source and target actors using a face reconstruction approach. The resulting parameter vectors represent meaningful semantic dimensions such as the head pose, facial expression, and eye motion. These can be directly transferred from the source to the target. Next, we render synthetic images of the modified target actor rig. Finally, we employ our novel rendering to video translation network that converts space-time volumes of such conditioning input into photorealistic video portraits. We now show more full head reenactment results. Note that our approach only requires a few minutes of training data for the target actor and thus can even be applied to internet video footage. The reenacted output videos have a high level of realism. In addition to the head pose, the source actor can also control the facial expressions and the eye motion, including eye blinks. Here is another result with different source and target actors. Please note that also the upper body, hair, and scene background are consistently synthesized to match the new head motion. Even the shadow in the background moves consistently with the modified foreground. Our approach can also be applied to facial reenactment by transferring only the expression parameters. As can be seen, our approach nicely transfers the expressions. Using our approach, we can also provide interactive user control over video portraits. This enables live modification of the rigid head pose, facial expression, and eye motion. All parameters can be controlled independently or simultaneously. Similar edits can also be applied to video content. Here, we selectively remove the facial expressions or head motion of Theresa May. Next, we compare to the state-of-the-art facial reenactment approach of Tees and colleagues. In comparison to their face-to-face approach, our result better matches the source facial expression while also correctly transferring the head motion. This enables a whole new range of video editing capabilities. We also compare to the audio-based dubbing approach of Suvayano Kwon and colleagues, which produces accurate lip sync.
Especially our friends who are lesbian, gay, bisexual, or transgender.
Their approach does not have explicit control over the facial expressions, and therefore the output doesn't always match the expressions of the source sequence. In contrast, our visual dubbing approach accurately transfers facial expressions. In addition, our approach provides additional control over the head pose and eye motion.
Especially our friends who are lesbian, gay, bisexual, or transgender.
Even professional dubbing of foreign language movies, like this German to English dubbing, leads to bad audiovisual alignment.
My first time on stage was in 1998.
Our approach modifies the face to match the new audio track at high quality.
My first time on stage was in 1998.
In terms of audiovisual alignment and synthesized mouth interior, our results are significantly better than Garrido and colleagues on the right.
My first time on stage was in 1998. Have you eaten, Mr. Angier? I need something impossible. You're familiar with the phrase.
We also compare to the image reenactment approach of Averbuch, Elo and colleagues. Our approach enables more significant modifications of the head pose, while their warping-based approach distorts the head and the background. Note that their approach is based on a single target frame, while we learn from a video clip. We evaluate our approach quantitatively in a self-reenactment setting, in which the source and target videos are taken from different parts of the same video. The error map shows the per pixel root mean squared error in RGB color space with respect to the reference. Our results are nearly indistinguishable from the real video. We next evaluate our space-time conditioning strategy. Our novel space-time conditioning significantly improves the temporal stability of generated videos and leads to a much smaller photometric error. We also evaluate the required size of the training corpus. The quality of results improves visibly with larger training sets. The best results are obtained with a full dataset. We now evaluate different resolutions of the training corpus. The quality of results is comparable for different image sizes. However, due to significantly faster network training, we use a resolution of 256 by 256 pixels for most of our results. We also compare our method with nearest neighbor retrieval. Our approach is trained to generalize the pose and expression spaces, and thus it is temporally coherent and better reenacts the source actor. Our approach works well within the span of the training corpus. Head poses or strong facial expressions outside the training corpus can lead to artifacts. This is a common limitation of all learning-based approaches. Here we show an additional high-quality interactive face editing result. We first change the head pose. Notice how this produces varying plausible upper bodies. We next modify the facial expression by lifting the corners of the mouth. We can even perform significant modifications of the facial identity. Thank you for watching.